What is the probability that the numbers 4, 8, 15, 16, 23, and 42 are drawn out in this order if the ball that you choose is not returned back into the box, and if it is returned back into the box before you chose another one? So I draw out a 4, I throw it back in, and I draw another one. That's the second scenario. First scenario is I draw out the 4 and it's done. And then the next ball I draw out is an 8. So in the second scenario, I can put the 4 in, and that changes the probability a little bit because I could draw that ball again on accident, right? So how would we calculate these? Let's look at the first one. Let me break it up here. What's our event, first of all, for each of those? I want to draw 4, 8, 15, 16, 23, and 42 in that order.
1.
Yeah. There's only one way to do that, folks. There's only one way to do that, yeah. No matter how you slice it, that's it. That is the event that I want. I want to draw out those 6 numbers. What's the sample size on the first one? The first one is sampling without replacement is what you call that. And the second one is sampling with replacement. Okay, do you see why those words are chosen, right? So the first option is there's 50 ways for both of them. What about the second scenario? You said it, Jace, you said the second number for the top one was what, 49? What about the bottom number? It's 50 again, right? It's 49 and then 50 for the bottom one. And then it's going to be 48, 47, 46, 45, and so forth down the line. Or in the case of the bottom one, it's 50 every time. Because every time I throw the ball back in there, I'm back to 50 choices again, right? So this top one, 50, 49, 48, 47, and so forth, what is that? That's a permutations problem, right? That's a 50 permute 6 problem, right? 50 permute 6 at a time, right? Arrange 50 things 6 at a time. That's what that is. Those are our final numbers, and we divide them by, or 1 divided by those, and we get these as our final probabilities. Not very good. Again, the journey is the point, not the actual questions. Okay, we feel okay about that? So let's look at this idea briefly of complements and unions. This is the probability of an event not occurring. Right, so just simple mathematical basic terms. If we know the probability of an event occurring, don't we also know the probability of that event not occurring? What is it? What's the probability of all scenarios occurring and not occurring? 1, right? It's 100%. You flip a coin, 100% of the time it will be tails or heads, right? Even if it's a weighted coin. Even if 75% of the time you're going to get heads and 25% of the time you're going to get tails, 100% of the time you'll get one of those too, right? No matter what. We're going to rule out landing on its edge, let's say, right? But if you add that in, 100% of the times you will get edge, heads, or tails, right? 100% of the time. So the probability of an event not occurring is the probability of it occurring subtracted from 1. Very simple, right? But this can be a very useful tool to us. So if E is the event, then S minus E is not the event. In other words, it's not E, or complement E, right, from our set theory, okay? Thus, we have the probability of the complement of E, or of the event not occurring, is equal to 1 minus the probability of the event actually occurring. Make sense? It's pretty simple. These concepts are, most of them are relatively straightforward, but when you start putting them into formulas and formalizing them, and you have to learn the language, the academia language, it gets a little tricky sometimes. But just remember the basic concept here. So why can this be useful? Let's look at that. Well, what do you guys think? Here's one scenario, okay? Let's take a sequence of 10 bits that's randomly generated, right? So 0, 1, 1, 0, 1, 1, 10, 10 things. What is the probability that at least one of those bits is a 0? Now think about how you would solve that problem. Don't try to calculate, but just conceptually, what would you have to do? What's the probability that at least one of them is a 0? Well, I have to calculate the probability of only one being a 0. Then I have to calculate the probability of 2 being a 0. And then I have to calculate the probability of 3 zeros and then 4 zeros and add all those up, right? But also, what is the probability of one of them being 0? Well, it's where the first digit's a 0, or the second digit's 0, or the third digit's a 0. That's a lot of stuff, right? Well, there's an easier way to do it. If we just figure out what's the probability of it not having any zeros, right? Because we're asking at least 1 0. Well, what's the probability, what does it look like, of having no zeros? That's where it's all ones. right? So what is the event in this scenario if we weren't going to use the not event or the complement of the event? It's all that stuff I just said. It's very tricky. Sample space is easy enough to calculate, right? It's 2 to the 10, right? Because we have 10 bits and there's 2 options for each bit, right? 2 times 2 times 2, 10 times, okay? But the event size, that's where it's tricky. So what we can do is, well, what is not the event? What's not the event? Everything being ones. And how many ways can you do that? One way, right? That's a lot less things to think about, right? So, again, we discussed the deals with E. And so we'd have to look at every one of those scenarios that I just talked about a minute ago, or we can just look at the complement of E, which we decided is 1, right? The event that all 10 bits are 1. And there's only one scenario where that happens. So that means that the probability of the event not occurring is 1 minus the probability of the event occurring, right? Which we know this, that's our basic formula. Well, algebraically, we can rearrange that to be the probability of the event occurring is 1 minus the probability of it not occurring. Well, what's the probability of not occurring? 1 over 10 to the 4, or 2 to the 10th, right? Minus, so 1 minus 1 over 1024, which means there are 1,023 divided by 1,024 ways that you'll get at least 1 0, which is 99.9% approximately, which makes sense, right? This passes the sniff test. But do we understand how that calculation works there? Do you see why, knowing that little simple formula, that the probability of all events and non-events together will always be 1? It's a very useful tool for figuring things out. So let's think back to our basics of set theory. We learned that the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. Remember that? We talked about that a few days ago. All right, so we can apply this to probability. We can figure out what's the probability of event A occurring or event B occurring. So we get this. Look at this formula closely, all right? The probability of event 1 or event 2 occurring, right, that's what the union is equal to the probability of event 1 plus the probability of event 2 minus the intersection of the probability of event 1 and 2. So let's take a quick sample here. What is the probability that positive integers selected at random from the set of positive integers in the next thing 100 is divisible by 2 or 5? Right, so I pick any number between 1 and 100. What's the probability that's divisible by 2 or by 5? That's what I'm asking. Not both, just one or the other, okay? So what is our E here? It's really, we have an E1 and an E2, right? What's event number 1? Yeah, it's the numbers divisible by 2, and then the E2 is the numbers divisible by 5, right? How many numbers are divisible by 2 between 1 and 100? 50, right? Yeah, all the even numbers. And then, of course, and then the union of E1 or E2 is that's the event that the number is divisible by 1 or the other of those two, right? And then the intersection is the event that the number is divisible by 2 and 5. Agreed? Which is, in other words, is divisible by 10. All right, so here we go. Here's our nice fancy formula for this. And again, if we just plug these in, what is our sample size? What is it? It's in our original problem. It's 100, right? E1 and E2, we already talked, it's 50 and then 20 for the number of numbers that are divisible by 5. There's 20 of those. And so this is what the formula looks like. It's 50 divided by 100, that's the probability of being divisible by 2, plus the probability of being divisible by 5, minus the intersection, which is 10 divided by 100, the probability of the intersection, which is 60%. How do we feel about that? Make some sense? Okay. To the whiteboards. So let's take a look and see how we did on these. What we have is a sample set that is sample space 1 through 6. And then we have event E, which is getting a 1, 3, or 5. Let's say we're rolling a die here, right? Event E is 1, 3, or 5. Event F is getting a 4, 5, or 6. And event G is getting a 2 or 6. It doesn't have to be rolling a die, but whatever, just getting those numbers somehow, whatever it means. What's the probability of E? I think that's pretty straightforward, right? It's, 3 out of 6, right? Easy. Probability of F, also 3 out of 6. Probability of G, 2 out of 6. Okay, I think those are pretty simple, pretty straightforward. I think we understand those. Okay, that's supposed to be complement E there and complement F, complement G. It looks a little funny. But what's the probability of not getting E? It's also 3/6, right? There's lots of ways we can do it. We could figure out what is the set, not E, and then run the calculation, or we just 1 minus 3/6, right? 1 minus this, where's my mouse at? 1 minus this right here, right? And the same thing here, and we will see again, it'll be 3/6, 3/6, and then the last one is 4/6 because 1 minus the event G occurring is 4/6. Simple enough, right? I figured those were not a big deal. Look at the next ones are a little trickier though, okay? The intersection of E and F. What is the intersection? Forget about the probability. What's the intersection of E and F? Yeah, what is it? No, what's the actual intersection of the sets? Yeah, just the number 5, right? So there's only one event that is both E and F, right? So that's 1. And then E and G, there's only one event that is, or sorry, there is no events that are E and G, right? Do you see that? And F and G, there is one event, right? So when you do the math, you get 1 out of 6, or 0, or 1 out of 6. Pretty simple, right? Last two. What's the union of E or F? Well, it's 1, 3, 5, 4, 5, 6, right? Of course, we're dealing with cardinality, so there are 5 possible outcomes there, right? So it's 5 out of 6. And then what's the probability of that not occurring? 1 out of 6, right? Pretty simple. Feeling okay about that? So here's the one I was talking to you about earlier that we have with, we're using the actual decimal numbers here that we're going to do as we go along. So these statistics I think are actually true. And I don't know why that says apostrophe there, but 10% of Americans have diabetes. That should not be apostrophe there. 30% have high blood pressure. 7% have both. I used to be one of those 10%. I have reverse diabetes, no longer have diabetes. Hashtag keto for life. Still working on the blood pressure though. It's better, but it's not all the way there. Anyway, 7% of people have both. All right, what's the probability that an American has diabetes or high blood pressure, that an American does not have diabetes, and that an American does not have high blood pressure? These are the same things. We're using sets and complements of sets here, and the probability of events occurring and not occurring, right? It's all the stuff we've kind of looked at. Well, let's look at what we do know, okay? We know the probability of D, right? What is it? D being diabetes. 10%, we know that one. We know high blood pressure or hypertension, that's H, just 30%. And then both is 7%. Those are given, right? We already know these numbers. But what's the probability of duh? D union H, that looks like duh. What's the probability of that? Using our formula, right, we get 30% plus 1%, 0.1%, or 10%, sorry, minus 7%. Which gives us 33%. Make sense? That's just using the formula from earlier. But it's the probability of us having diabetes plus probability of us having high blood pressure minus out where the intersection of both. Because that just gets rid of duplicates when you're doing counting, okay? And if that's fuzzy, go back to the set theory videos. Next one, probability of not having diabetes. Well, it's 90%, right? Just 1 minus 10%. And then not having hypertension is 70%, okay? So in other words, I grabbed a random American off, because these are American statistics, grab a random American off the street and just, all right, does this dude have diabetes or high blood pressure? That's what I want to know. If he has both, then he has diabetes or high blood pressure, right? Yeah. And so I want to know, just this random guy, does he have one of them? And the answer is yes. The fact that he has both, he still has one of them, right? So that's what this kind of question is asking. Right? Because what's the probability that he has both? We already know, 7%. Probabilistic reasoning. This is the idea of probabilistic reasoning is where you're not so much using a formula as you are using, you're understanding probabilistic ideas, probability ideas, and you can apply them in the real world. Not so much, oh, I'm going to calculate this probability to choose this decision, but it's more just sort of like wisdom. You kind of have this wisdom because you understand probability, right? And one of the most famous examples of this is a real thing, and it's the Monty Hall problem, right? There's a game show that started in the 70s called Let's Make a Deal. It's currently hosted by Wayne Brady, dude from Whose Line Is It Anyway? I think they may have changed out who it is. I haven't seen it for a while. But in the 70s, it was by Monty Hall was the guy's name. Here's the basic idea. He's going to give away a car. He has 3 doors, and he's going to hide behind one of the doors a goat, an actual goat. They had real life goats on there. It was always, but it wasn't always a goat, but it would always be some sort of ridiculous prize, right? Like a broken down car without an engine or something, that's some crappy thing that you did not want. There'd be 2 of those, but often it would be an actual farm animal, an actual goat, and then one of the doors would have a real prize in it, okay? But they're hidden behind the doors. Now, they're not necessarily in the same spot there. They're the same spot, maybe they're not. But they'd be behind the doors. Now, the contestant would get to choose a door. They would choose a door, and then once you chose the door, the host, who knows where everything's at, would open up one of the other doors to reveal a goat, right? And then it would ask you the question, do you want to change which door you chose? Do you want to change to the other door you haven't looked at that hasn't been opened, right? That's the basic idea. So we're going to kind of walk through what this is like here. So let's say we chose door number 2, okay? And I think I did leave the prizes where they're at, where they were in the previous slide. So then he decides to reveal to you that there is a goat behind door number 1. Then he asks you, do you want to change to door number 3? That's his question to you, okay? We know what's behind there. Yeah, I probably shouldn't have revealed it already. But the person playing the game does not know what's behind there, okay? So the question is, do you want to change your mind? Now, imagine you didn't know the goat was there. Do you want to change your mind? Does it matter? And I think you already know the answer to this, so as I mentioned earlier, you don't get to play. Have you seen this before too?
No, it's up, I know it.
Okay. What about you, Yuri? Do you know this one? Okay, so I'm going to ask you. Does it matter if you change your mind to door number 3? Now, I've revealed where the goat is. Obviously, you'd want to pick 3 in this case. But if you didn't know where they were, does it matter to change your mind?
No.
Okay, so that's where the debate came in. And you're going to say that it does matter, right? Okay? You're probably thinking, well, it's just a 50-50 chance. It's either behind door number 2 or behind door number 3. It's 50-50 chance. But the truth is, that's actually not the probability. And this was the big debate where it was amongst mathematicians in the 70s and in the 80s. And there's still a few people that haven't bought into this yet. But it's been proven that this is true. And I'm going to show you a little proof in a minute. Not a proof, but I programmed this to work in a minute. So here's the idea. Should you change your mind, and does it matter? And the answer is yes, it matters, and you should change your mind. And here's why. Okay? Let's pick a door. We're going to go with... I don't think this is just, I think we're just going to play along. I didn't make any slides of you picking doors, I don't think. Let me just look and see what the next slide is, yeah. Okay, so just pick a door. We don't know where the prizes are. I'm not predicting what you're going to pick, no magic here today. But pick a door, anybody, just pick a door. 2 again, okay. So this is the door we chose. Now, right here, we're choosing number 2. My question to you is, what is the probability that you chose the correct door? 1/3. So 1/3. 1/3 is the probability that we got it correct. 2/3 of the time we will be wrong. All right. So I'm now revealing that we chose number 2 a moment ago. We were just playing along. We chose number 2. This is not revealed to the contestants, but I'm revealing to us as a class where the prizes are. We chose number 2 a minute ago. Well, we were wrong, right? Because 2/3 of the time we will be, right? So if 2/3 of the time we're wrong, in this scenario, the game show host will reveal door number 1. He will show you that it's a go. He's not going to reveal door number 3, obviously, right? Okay? And by the way, when he reveals door number 1, you can still pick number 1 if you wanted to. If you wanted a goat, you can pick it, right? So that's why he's not going to reveal door number 3, because you're going to be like, oh, I want that one, right? I want the car. So he's going to reveal one of the bad prizes. No matter what you pick the first round, one of the remaining doors will have the booby prize, as they call it in there, right? One of them would be. So he's gonna reveal door number 1. Those are the 2 bad ones, right? 1/3 of the time you will correctly pick the right one, but 2/3 of the time you will pick a goat. So he's going to reveal to the contestants that that's a goat. We picked number 2, that's a goat on the left there. Well, now this is where the debate comes in. Some people say, well, the probability now that I'm right is 50-50, but it's not. It looks like it, because if the game started with only 2 doors, the probability would be 50-50 if you picked one. But the probability that I'm sitting on a wrong door is 2/3 chance, 66%. I'm most likely on the wrong door. I'm better off changing my mind, because most of the time I will be wrong, and so changing my mind means 66% of the time when I change my mind, I'll win. Now, obviously the catch is you only get to play the game once. You don't get to play it a whole bunch of times and play the odds, right? You only get to play it once. So I'm better off changing my mind to door number 3, and as you can see in that case, we would have won if we did that. Yeah, we win because we changed our mind. Okay, does that concept make sense? To the code, I actually coded this up. So what I have here is a simulator that will allow me, like right now you can see the number here, it's whatever that is, 100 million or whatever. It will run the game 100 million times. The game will automatically randomly hide the goats and the car, or whatever. I have car and goat as the prize and the booby prize there. It'll automatically just randomly assign those locations. Then the computer will randomly choose a door, and then because I have my variables set to swap being false, it will not swap the door after one of them's revealed. When we run the numbers, you'll see that most of the time it will lose, right? So let's start small. Like, let's just run it 10 times, and I'm gonna make swap true, okay? So what this means is when you play the game, every time, all 10 times, the person will guess a door, and then it'll swap doors once the goat is revealed, right? So here we go, run it. And you'll see they won 70% of the time by swapping. Now, if I run it a bunch of times in a row, you'll see there will be some, like there's a 50-50 there, 60-40, 70-30, 50-50. You will find some that'll flip the other way, 80-20, 100% of the time, wow. 60-40, 40, so there's one, 40-60, right? This is dealing with an idea that I don't think we really get too much more in depth, maybe a little bit later, but the law of large numbers. The closer you approach, the more you approach infinity, the more the probability becomes more accurate. So if I could run this an infinite number of times, it would be dead on 66 point whatever percent versus 33 point whatever percent. But if I only ran it once, right, you're gonna see 100%, 100%, 100% loss, right? Well, that's not useful. I flip a coin one time, it lands tails, therefore it's tails 100% of the time? No, obviously not, right? So the law of large numbers says if we run it a few more times, let's go 100, and you'll see that it'll get a little bit more accurate, 63, you'll see most of the time we're gonna win here, okay? But watch this. If I do a large number here, I think that's good enough that it won't take too long. Look at the calculation, 66.7. It's 66 point something every time. You'll never see it the other way. You'll never see a scenario where you have more losses. It'll always be 66 and 33 if I run it that many times, okay? The law of averages plays out, the law of large numbers. And it shows me how many games I played, 1 million games. If I make it to where he does not swap, by the way, if you guys want this code, I'm happy to give it to you. It's just one file here, it's pretty small. If I run it where they don't swap, you will see that every time they will lose. Or 66% of the time they will lose, 2/3 of the time. Because 2/3 of the time you chose the wrong door and you didn't swap, so you're still stuck in that wrong door, you chose 2/3 of the time. So let's do 100 million, see if that'll run. But look at how dead on that is. 66.67, 33.33. That's exactly 1/3 and 2/3. That's exactly that. I'm just gonna run it one more time, see if we get the same thing. Yeah, it's right in there. Anyway, we've covered all this stuff here today, and I appreciate you guys sticking around for the extra time here. Next time, we're gonna get into conditional probability, which is What is the probability that this event occurs given that this other one already did occur? Which can answer some of these questions you were talking about. What's the probability that I have diabetes given that I have hypertension, right? You can look at those kinds of things. Any questions about anything we covered today?